Hello and welcome to this clip on introducing you to carbonyl compounds. We're going to look at the origin of the carbon double bond oxygen bond, an example of true carbonyl compounds as opposed to those that just happen to have the C double bond oxygen somewhere in the structure. We'll look at how we make carbonyl compounds through the oxidation of alcohols, how we test for them using Tollens reagent and 2,4-dinitrophenylhydrazine, and how this allows us to give a positive identification of the carbonyl compound without having to go down the route of spectroscopic analysis. And then we'll look at a worked exam question to illustrate some of the ways you might be tested on this area. For this clip, we'll assume that you're already comfortable with oxidation of alcohols and the associated chemistry from year 1 of your A-level chemistry course, so we won't be spending too much time reviewing that. It'll assume that you're already quite confident on that from last year. So we start off by drawing in a sigma bond between a carbon and an oxygen atom. The next thing we do is we add dipoles. So oxygen is more electronegative than carbon, so oxygen is going to be delta minus and carbon is going to be delta plus. I'm also going to add the other bonds that the carbon atom is involved with. It's not just carbon sitting there by itself. There's also 2 other bonds it will be involved with as well. And these are also sigma bonds. So what we now have to do is add in the p orbitals on the carbon and oxygen atoms. So don't forget that the p orbitals are above and below the plane of the already existing carbon single bond oxygen. This is where it turns into a carbon double bond oxygen because those orbitals overlap sideways. So what happens is the sigma bond that's already there tends to draw the carbon and the oxygen closer to each other, and as that happens the sideways overlap of the p orbitals that are already drawn in takes place. So this gives rise to sideways overlap of the p orbitals. And if you notice, the electron density of the pi bond is slightly shifted towards the oxygen because the oxygen is more electronegative. Carries the delta negative sign, so it's a dipole. And we have sigma bonds I should say, around the carbon, 2 at one end which will be bonded to other atoms, and then there's 1 between the carbon and the oxygen. So what does this give us in total? So we end up with a trigonal planar setup, carbon double bonded to oxygen, formed by 1 sigma bond and 1 pi bond. The carbon and oxygen bond is polar, and you have 120 degrees around the carbon atom, 120 degree bond angles. It's important to remember as well that the only true carbonyl compounds are aldehydes and ketones, because if you have a closer look, you'll see that the atom that's actually bonded to the carbon as part of the C double bond O is either carbon or hydrogen. And what this means is that the polarity of the C double bond O is not disrupted. In the examples further down, all of which you'll come across in A-level chemistry, you'll see that there's actually another atom that's actually bonded in each case. It might be an oxygen, a nitrogen, a chlorine, for example. All of these are electronegative atoms, and therefore what they're going to do is they're going to affect the polarity of the carbon-oxygen double bond. So in other words, the polarity of that particular part of the molecule is going to be disrupted in some way by the presence of another electronegative atom that's actually attached to the same carbon. So for that reason, the compounds along the bottom are not true carbonyl compounds and don't exhibit carbonyl behavior. And this can be proven when we actually carry out specific tests for carbonyl compounds. The compounds that are listed along the bottom, carboxylic acids, amides, esters, acyl chlorides and anhydrides, do not respond to diagnostic tests for carbonyl compounds. So you might recognise these from your work on alcohols and their oxidation last year. So basically a primary alcohol, when it's oxidised, usually using K2Cr2O7 in the presence of an acid, will give you an aldehyde and water. And similarly with a secondary alcohol, if you oxidise that, you'll get a ketone instead, plus water. This is the easiest way to synthesise carbonyl compounds. Like I said at the beginning of the clip, I'm not going to go into details of distillation or refluxing, etc. That's covered in a separate clip, and I'm expecting that people who are watching this will have maybe done oxidation of alcohols earlier in their course. So this is just a reminder, really, of how you actually make them, what the chemical reaction is. So the first test we can use for carbonyl compounds is specific to aldehydes. We use something called Tollens reagent, which has to be prepared freshly. It isn't stable if it's stored, because you get explosive silver compounds forming. So therefore what we do is follow this method. We add sodium hydroxide dilute dropwise to silver nitrate solution until a brown precipitate of silver oxide forms. We then add dilute ammonia until that precipitate dissolves, and if that mixture is now added to an aldehyde, a silver mirror forms on the inside of the reaction container. I'm just going to play a short video clip I took of when I did this a couple of years ago, but it has to be done inside the fume hood because of the aldehyde vapours. So you can see clearly that the silver mirror that's formed on the inside of the test tube is a positive indicator that an aldehyde was present, and the aldehyde in this particular case was propanol. I thought I might add a little bit of chemistry here that carries across to your work you'll be doing with transition methods. If you're reading or looking at this after you've done your transition methods work, you'll recognise the silver diamine complex. So basically, Tollens reagent is a mild oxidizing agent, and as you know, aldehydes oxidize further to produce carboxylic acids. If you remember your alcohols oxidation reactions from last year. Ketones don't do this, so therefore ketones don't respond to the Tollens test, only aldehydes do. So it's a good way of telling the difference between an aldehyde and a ketone. So basically what happens is your silver ions that are still ionic in their nature from the silver oxide will form a silver diamine complex with the ammonia. That's what happens when the ammonia dissolves the silver oxide in step 2 of the method on the left. So the silver ion in this complex is then further reduced, or easily reduced rather, by the presence of the aldehyde functional group. And what happens is it forms silver metal, and the silver metal is your deposit of silver mirror on the inside of the test tube. So the other test for carbonyls is the 2,4-dinitrophenol hydrazine test. It's called 2,4-DNP for short. In the photograph on the far left you can see that there's a yellow liquid in the test tube it's quite toxic, it's quite poisonous, and we need to handle it carefully if we're doing this test. So it forms an orange precipitate if a carbonyl compound such as an aldehyde or ketone is added to it. So the precipitate, known as a 2,4-dinitrophenol hydrazone derivative, will have a very sharply defined melting point. Obviously the melting point can be measured in the laboratory quite easily using melting point determination apparatus. Once its melting point has been determined, that can be checked against the databases of melting point data to confirm the original carbonyl compound's identity. And the key point here is that it doesn't need to use spectroscopy to confirm it positively. So this is another way of deciding exactly what carbonyl you have. It's slightly more versatile than Tollens reagent because you can use it for aldehydes and ketones as opposed to just aldehydes, which is what Tollens reagent tells us. Aldehydes and ketones can also be reduced in the same way that alcohols can be oxidized to make them. So it shouldn't come as any surprise to see that you can reduce an aldehyde back down to its original primary alcohol, and likewise you can reduce a ketone back down to its original secondary alcohol. What's quite interesting though is the use of H to represent a reducing agent. In the same way that O in square brackets represents the use of an oxidizing agent, H in square brackets signifies the use of a reducing agent. Now, because technically hydrogen is actually being added, you can pause the video and just count the hydrogens on the left on the aldehyde and then count the hydrogens on the right on the propan 1-ol, for example. You have to put the number of hydrogen atoms added in front of your H in square brackets. So in this case, because 2 hydrogen atoms are added, you have to put a 2 to the left of the H in square brackets. Let's have a look at the mechanism by which this reduction takes place. It's probably a good idea to introduce a particular nucleophile called a hydride ion. It's basically a hydrogen atom that's picked up an extra electron. Now, the creation of the hydride ion has to take place under certain conditions. It's not a common ion, as you'd expect. Most of the ions that you get from hydrogen will be H+. So the H- ion originates from a specific type of reducing agent. So the name of this specific reducing agent is called sodium borohydride, and it has to be an aqueous solution for this particular mechanism to work. You don't need to know very much about it, but just for curiosity's sake, I'll take you through what the borohydride ion looks like. So it's basically a boron atom with 4 hydrogens around it, one of which is dative covalently bonded. But look at how the actual bonding works. It's not that it's datively covalent bonded with the boron giving 2 electrons or donating 2 electrons to the bond. It's actually datively covalent bonded with hydrogen donating 2 electrons to the bond, which is quite unusual. So therefore this is a source of the H- ion. So this part generally doesn't come up, as in this particular ion and how it's put together and its structure. It generally doesn't come up on A-level papers as something you have to know, but it's worth having a quick look at it anyway, just so we can understand a little bit more about where the H- comes from. So let's now move on to the mechanism itself. Before I do so, I'd like to draw your attention to a couple of top tips to remember when doing any mechanism in organic chemistry involving curly arrows. At the bottom of the screen you'll see that I've put that the curly arrow should either touch the bond it's coming from. Let me give you an example. Or the double head of the curly arrow should point directly and clearly at the atom the electron pair is moving towards. Let me give you another example. If the curly arrow starts from a lone pair, it should start from between the lone pair, like so. So just a few tips there to remember how to get maximum marks and not make your mechanisms look ambiguous. So let's start with what's going on here. The first thing to happen is the hydride ion attacks the delta positive carbon and forms a bond. The next thing that happens is the carbon now has 5 bonds, so it can actually lose one of the bonds that it had originally. So the next thing to look at is step 2, the pi bond on the carbon-oxygen double bond here breaks heterolytically and the oxygen atom gains a negative charge here. The intermediate reacts with a water molecule, hence why the NaBH4 had to be an aqueous solution, because water actually gets chemically involved in this particular mechanism. So the oxygen that's now become negatively charged now is a lone pair, and a lone pair can get involved in reacting with the water, as you'd expect. And finally your organic product is formed. In this case it's an alcohol, because the species you were reducing was an aldehyde. If it was a ketone, you'd be forming a secondary alcohol. And an OH group comes off, an OH minus ion is generated. So this is usually a 4-mark answer. You get 1 mark for your dipole and the pi bond breaking. You get 1 mark for the curly arrow correctly coming from the hydrides, either the negative charge on the hydride or in between the 2 electrons of the lone pair. You get a mark for showing what happens when the intermediate reacts with the water, and you get a mark for correct product. So just to reiterate, mark 1 is for the correct curly arrow from the lone pair of the hydride or from the negative charge of the hydride, pointing to the correct carbon. That's the delta positive carbon. The second mark is for the correct dipole and curly arrow showing the heterolytic breakage of the pi bond in C double bond O. The third mark is correctly showing the intermediate reacting with the water molecule. And the fourth mark is correctly showing the organic product and the hydroxide ion that's produced. So let's now try past exam question. We're looking at something called hydroxyethanol, and what's really interesting is the fact that it actually contains 2 functional groups. If you look closely, you'll see that you've got an alcohol and also an aldehyde. So be very careful on this one. It's designed to try and catch you out. So it says a biochemist investigated some redox reactions of hydroxyethanol and found that several different products were produced. Now I forgot to mention that the question actually tells you that there's an aldehyde group and an alcohol group. So I'm just going to put that information highlighted there for you. So it says, state what the biochemist would see when hydroxyethanol reacts with Tollens reagent. So they're not asking you to say what the actual product would be, they're just asking you to say what you'd observe, what you'd see. So obviously, like we've said earlier, you'd get a silver mirror. Then it's asking you to write the structural formula, but it actually says specifically the structural formula. So this isn't one of those ones where you can do part structural, part displayed, part skeletal, for example. So obviously when hydroxyethanol reacts with Tollens reagent, the aldehyde will be oxidized to a carboxylic acid. So your structural formula has to have a COOH or a CO2H in there somewhere. So the really important bit that should be in your answer is there and there. Notice that the primary alcohol is actually left alone. Tollens doesn't actually react with primary alcohols or secondary alcohols, it's only aldehydes that it reacts with. So leave the alcohol group alone when you're doing this. So then it says the biochemist also reacted hydroxyethanol with acidified dichromate by heating under reflux. And it asks you to write an equation with this oxidation. So if you remember, hydroxyethanol had some alcohol group in it, didn't it? It had an alcohol group at one end. It even tells you up at the top of the page. It has an aldehyde group and an alcohol group. So we've already dealt with the aldehyde group, now we can deal with the alcohol. So this particular equation, you'll notice you've got 3 oxygens, or 3 oxygens from the oxidizing agent. It's because what you're doing is you're oxidizing the aldehyde and you're oxidizing the primary alcohol. So don't forget, you have an aldehyde that's oxidized and a primary alcohol that's oxidized that produces 2 carboxylic acid groups. So it's really important to not get sort of tripped up by these types of questions where you can have more than one functional group being oxidized. Now there's options for partial oxidation here. Because it's a 2-mark question, you could get 1 mark for partial oxidations, but I'll talk about those when we have a look at the mark scheme in a second. The next thing that happens is the biochemist then reduced hydroxyethanol using aqueous NaBH4, which we've just talked about. So the part that's going to be reduced is obviously the aldehyde, so it's just this bit that's now reduced. The OH group on the other end is left alone. So that gives us a diol, doesn't it? Because it turns the aldehyde back into an alcohol group, and there was an alcohol group on the other end of the molecule anyway, so we now have two alcohol groups. So, it's a mechanism question to outline the mechanism for what went on. Use curly arrows and show any relevant dipoles. The number of times people still forget to do this is quite interesting. So please make sure you make this part of what you do. The curly arrows and the dipoles, please. So my first part, I've made sure that the curly arrow comes from between the two electrons of the lone pair on H-, and it points clearly to the delta positive carbon. When I'm breaking the pi bond heteroelectrically in the C double bond O, I make sure that the curly arrow touches the bond, comes straight off it, and points at the oxygen atom, that's delta negative. So the next part shows the correct intermediate, and again the curly arrow starts from between the two electrons of the lone pair that are now on the oxygen. They point to one of the delta positive hydrogens on water. Notice I've added in the dipoles to the water as well. And the bond between the H and the O in water is broken by showing a curly arrow starting from the bond itself, touching the bond, and pointing towards the delta negative oxygen within the water molecule. And finally I put in my correct product, my diol, which is my organic product, and also my hydroxide ion, OH-. So now let's have a look at the mark scheme. So we got silver mirror as our expected answer. We got the carboxylic acid group being produced from oxidation of the aldehyde. We got our reagents and both products. And like I mentioned, there were a number of different possible options for getting 1 mark, but these would be partial oxidations, not full oxidations, so obviously you wouldn't get the 2 marks for putting them. We said that we'd get a diol, and we were told here that we can allow skeletal formula or displayed formula, but do not allow molecular formula because C2H6O2 isn't actually specific enough to say that it's a diol, because you need to show somehow that the examiner can see that you know it's a diol that's made. So in the description we did our curly arrow from hydrogen, or H-, the hydride ion, to the delta positive carbon. We did a dipole and a curly arrow from the C double bond O to oxygen. We drew the intermediate, and we showed the curly arrow from the intermediate to H delta plus in water, and if H2O is used it must show the curly arrow from the OH bond to the oxygen. We did all of that, so we're fine. There are fusions, so any of these could also work. So if you wanted to have a little look at these, what I'd possibly suggest at this point is not trying to get too confused by all the different options that are in front of you here. I would stick to the one that we did earlier and just make that the one that you go and learn. In this particular mark scheme they allowed these options because they're legitimate, but don't go and try and learn 3 or 4 different ways of getting the same marks. That's what my advice would be at this point. Obviously when you go and try past paper questions, you'll come across mark schemes that go with them, and those mark schemes may have several different alternatives. What I'm trying to say here is don't get confused if you see several different alternatives. Stick to the one we've covered in this clip and the one that your teacher's covering in your lessons, and you won't go far wrong. The main thing is to make sure that your use of curly arrows and your use of dipoles is accurate. That's where people lose marks in mechanisms. Okay, so hopefully this was a fairly useful introduction to carbonyls. Please don't hesitate to contact one of us at college if you need a bit of further clarification. have a chat to your teacher. Maybe you'll come to one of the subject extensions. In the meantime, thanks for your time, and bye for now.